Good morning, Code Milkers. Today we have the final grand finale of the 30-day Leak Coding Challenge for April. In case you didn't know, it's been announced there is the 30-day May Leak Coding Challenge. So I'm probably going to do videos for those also. I'm not sure yet. I have a day to figure it out though. Today's problem was check if a string is a valid sequence from root to leaves path in a binary tree. This, I think, took the award for longest name in a problem ever. I think they could have condensed that down, but anyways, given a binary tree where each path going from the root, it's important, from the root to any leaf form a valid sequence. Check if a given string is a valid sequence in such a binary tree. We get the given string from the concatenation of an array of integers r and the concatenation of all values of the nodes along a path result in a sequence in the given binary tree. So it might be confusing in this problem because they keep saying string, and if you look at the inputs, there are no strings, there's just two arrays. So I'll explain right now what they mean by string. I think that's the way that the interpreter or the compiler in this problem looks at the binary tree sequence. I'm not sure exactly why, but for this problem, don't think of it as a string. Don't worry about it. Just treat it like the input array that it is. Don't worry about it being a string. It'll only trip you up. So I'm going to explain what a sequence is in the context of this problem. So we have this binary tree dictated by this array, and we have the sequence we want to find in the array input, which is the second parameter. So the sequence of nodes we want to find is 0, 1, 0, 1. So that means starting from the root has to be 0. We can't pick up at some node that's a descendant of the root with that value and count it as the first index. We have to start from the root. So, and that actually makes this problem easier because it eliminates the need to recurse beyond once you find something that's out of the original sequence. So I'll do a drawing of why that's true after I explain this one problem. So this one actually returns true because it does have a valid sequence starting from the root and ending at a leaf node. Leaf node meaning there are no children off of it. It just has a left child of null and a right child of null. So if we start from the root node, we have 0. And then once we go down to the left child, we have 1. And then we go down to the left child, and it's 0. It is 0. And then we go on to the fourth and the last child, which is a leaf node, and it's 1. So if 1 hadn't been the leaf node here and we had 1 more, which had been 0, this would not have been a valid sequence because the last node in the sequence must be a leaf node. So let me do a drawing on the whiteboard. So let's say we have the following simple binary tree. We've got 1, 1, and 0, 0, and we're looking for the sequence 0, 0. Okay. So since we're looking for 0, 0, we have to start at the root node. No, we don't start at null, hopefully. So we start here. Does that first index, the 0th index of our sequence, match the root node value? The simple answer is no. So we can actually just return from there because it's not equal to it. So we don't need to recurse further. We don't need to check and see if some child of the root node has that correct starting root node value. We have to go from the original root. So let me break down my solution. because we've explained the problem pretty well. So I went off both of the hints in this problem just because I wanted to see what they thought of it. I was thinking of doing a depth first search anyway, so this only confirmed it. So we're given the isValidSequence function, and like I said, we're given a root, which is the binary tree represented in array form, and we also have the R parameter, which stands for the given sequence we have to match starting from the root. So here is the depth first search function, which if you remember, it means we're going all the way down a single path to a leaf node. We're not going by levels, all the nodes in a certain level of the tree. We're going all the way down and then all the way down, all the way down, and then back up. The only code we're returning in this is the DFS starting from the root and with index 0. Now this index parameter in the DFS function stands for the current index we're at in the array parameter, or the array sequence that we're looking for. So at a given level of the depth first search, we have a certain index we want to be checking. And this works throughout the whole tree. So starting at the root, we first check if the node is null, which means there is no binary tree, or if the current node's value is not equal to the index of the array. So if the given index of the sequence we're looking at does not match the node we've reached in the tree, we know to return false. We don't need to check any further. Now, that's our first base case. So we know to return false immediately after that, because that means our sequence is not matched. The second base case is once we reach the end of the sequence, because we have to be sure of one thing at the end of the sequence, and that is that the left and right child are both null. So the value of the current null has to be equal to the last index of the array, so the last element at that index, and then both of the children have to be null because it has to be a leaf node. And then we just return true or false based on that. So if neither of these base conditions is met, that means we have to recurse further, both left and right, to see if the path is reciprocated in either direction. So we go one index further, because as we go down in depth, we're increasing an index across the sequence. So we increase the index by one each depth level we go further in the recursion tree. So we go left, we go right, and then we either do left and right again, or we hit one of these base cases and then return the correct value. Now, as the recursion results, come back up the tree, we're either returning left or right, and we can use this implicit, I guess, like truth evaluation, because if left is true, which means that there was a valid sequence, that left is going to, I guess, like bubble up to the top of the recursion tree as true each time, because with an OR logical operator here, if the first operand is true, that one gets returned. But if it's not true, then we use the truth value, whatever comes after it. So right could be false or true, and we use that value in case left is false, and we know that. So either way, by the time we reach the root node, we'll have the truth value of either the left side or the right side. So we'll know if the sequence is valid once we reach the root. So we'll submit the code so you can see the time complexity here. Since this is a new problem, it doesn't have comparisons to other people's solutions yet, really. But it's a 96 millisecond solution, so it seems quick. It's probably in the 50%, 40% range of beating other JavaScript submissions. So As with other recursion examples, the memory usage could be better. But yeah, it's a cool question, and it's a great way to leave off on the April LeetCoding challenge. So thanks for watching. Hope you enjoyed.